So my name is Gage Erwin, and this is thermoelectric properties of Kagame metals, and let's get right into it. So what is a thermoelectric material? A thermoelectric material is basically a material that creates a high voltage when there's a small temperature difference, otherwise known as having a high Seebeck coefficient, which you can see right here. When multiple of these materials are put together, you can create a module like this, which you can make a thermoelectric generator. And when paired in electronics such as this watch, you can utilize these properties to produce electricity from your own body heat. So common goal is to develop new materials with improved thermoelectric properties to potentially be used in green energy applications and other applications. So what makes a good thermoelectric material? A good thermoelectric material is characterized by its ZT value, which you can see the equation right here. And you can maximize the ZT value by manipulating certain variables that you can see right here. Hence, we're interested in looking at 166 compounds, which you can see one right here that exhibit advanced physics phenomenons that increase its ZT value. One of these features is that a 166 structure tend to have Kagame lattices, which you can see at the top right, which tend to have hexagonal shapes. And potential theories suggest that these Kagame lattices feature phonon glass electron crystals, which tend to have minimized, minimized thermal conductivity without affecting electrical conductivity, which can maximize ZT value. Hence, we want to learn more about these properties and if it applies to our crystals and how to apply to other crystals. And if you look closely right here, you can see one of the crystals I grew. I know this is a 166. Oh, this is ytterbium, manganese, and germanium. So I know this is a 166 because it's hexagonal. And I also use energy dispersive spectroscopy to look at its composition, pattern XRD diffraction to look at its peaks to match theoretical data. And I grew this crystal using a common method known as molten metal flux growth method. And this is common because you can melt metals that melt at lower temperatures at higher temperatures and metals that melt at lower temperatures. So when it's molten, you can then cool it down so that the crystal grows inside the flux, similar to how crystals grow inside water. And the way that we grew it was that we packed in a certain ratio of the composition that we want inside of a crucible, and then we packed in a bunch of bismuth into it to act as the flux. Then we sealed it inside of a quartz tube under a high vacuum and placed it in the furnace so that it can grow. After which we centrifuged it to remove all the molten flux away from the crystal. After which we have a crystal. Now we can measure its physical properties. One of these physical properties that we measure would be magnetic moment versus temperature. And we can see that there is a complicated evolution of spins lining. As you can see at high temperatures, the spins are very erratic. They're not aligned at all. But as you decrease the temperature, it starts to increase and it becomes ferromagnetic, being ordered. And now that we have some information, we can ask questions such as, is ytterbium divalent or trivalent, and is it magnetically frustrated? In addition, we can also look at heat capacity to see if it measures what we would expect. And it does. And around 240 Kelvin, we can also see that it correlates with the magnetic moments. As you can see, there's some peaks right here and here, and that might suggest that there's a phase change. So we want to look closer at these temperature ranges to see if there's any interesting physics phenomena. However, this is still an ongoing project, and we still have to grow bigger crystals to measure the ZT value. So at this moment, I would like to thank Dr. Kaiaway and Dr. Bombach and everyone else in the lab, as well as the National Magnetic High Field Laboratory.